Hello guys, back to Maison African Motives, still on industrial electronics, working on N4 revisions. We've got the Kirchhoff's law and so forth that we are going actually the applications of Kirchhoff's law. So the first part we have got, okay, question number one, actually November 2017. Okay, so this one, it's November. That is November 2017 revisions. Okay, so let's see what we're given here. 1.1, we are given to explain the following laws of Kirchhoff's. Okay, of Kirchhoff, we have got the first part, that is the current law. So we're asked to explain what do we know about the current law. Okay, so if you have to check here, I've got some of the explanation that we can consider that when several conductors meet at a point, the total of the currents flowing towards that point is equal to the total of the current leaving the same point. If you consider this, let's say we've got, this is our junction here. So we can consider our currents on the junction. Okay, let's just say I've got, these are enough. So what it simply says is that if you consider there can be currents flowing towards, okay, let's say this is our current one, our current two, then we've got current three leaving and also current four leaving like this. If these currents are to be combined, everything must be equal to zero. But we can say these two currents which are flowing towards these ones which are entering, if we add I1 plus I2, this must give us these currents which are leaving, the ones which are pointing outside, that is I3 plus I4. All right, like that. So that is what we are simply having in this case. So you can just have it in a simpler way. But as long you understand this, then you can put it in words in a nicer way, like what you're given them. So let us not waste much time. Let's check the other part that we are given. This time we have got the voltage law. All right, the voltage law, still with the same idea. We have got here, if you check on the voltage law, that in any closed circuit now, the algebraic sum of the products of the current and resistance of each part of the circuit are equal to the resultant EMF in the circuit. So here I'm not going to explain much because this is the part that you're going to use actually in the second question. So I'm going to explain that part much when we answer the second question. But that is all about the algebraic sum, referring to the voltage drops that they are actually the same. I mean, if you add those voltage drops, they must be equal to the sum of the total. All right. On 1.3, this is the 1.2. This is the most part that is applying the second law, which is the voltage law. Consider the following circuit and calculate the current flowing through resistor R3 using Kirchhoff's law. Okay, this is our resistor R3. So you need the current that is flowing through this resistor. So what you need from your N3, guys, if you still remember, you need to focus on the part that you are calculating the current, which is the resistor R3. But if you are to check here, according to the voltages that we have, we can see that the V1 that we have here, this is the longer part of our battery. So this means that this is our positive, all right? Then we've got our negative here. So according to the current flow, it shall flow from the positive, meaning to say the loop that you're going to take, you consider the direction from the positive. So I'm going to take it from the positive in this direction. I'm going to consider this first as my loop. All right. So this is going to be my first loop, which is from A to B to E and back to F, and you got A like that. Okay. The same thing in the second part. You can even consider the whole of the second part just to avoid issue of adding or subtracting voltage sources like that. Avoid that. Okay. So take the second one, as you can see again here, this is your positive, your negative on the other side. So you can consider the direction from the positive direction in this way. So meaning to say this is going to be our second loop, which we can consider from C to B to E and back to D or to see them. All right, so these are the two loops that we can consider depending with which part that you understand. But if you are to consider these loops, I want us to check the current that is going to flow in the resistor R3. From the first loop here, we're gonna have the first current. So you can just say this is our first current in this direction. All right, so we can just say this is our first current. From the second loop, we can say this is our second current. As you can see, the direction positive, so it's going to flow in this direction. So this will be our current 2. Let's consider the first law. The first law, we talked about the current law to say these currents, if they flow towards a junction at B, they will be the same as the ones that are flowing from the junction, which is the one that is affected here. So this one is going to flow from the junction, which is the sum of these two currents which are flowing towards. This one is coming in, this one is coming in, but this one is going out. So meaning to say this is going to be our current 3, but we can just say our current 3 is equal to current 1 plus current 2. All right, that is the sum of these two currents. If you check here, so that is what you're going to have. And with this information, I think we're done. Let's just have our loops aside and have our answers or calculations. Okay, so the first loop, we are going to consider the loop A to B to E to F and back to A. So this is going to be A, B, E, F, back to A, or you can just end it. F is still one and the same presentation. If we consider this loop, remember from our second law where we are talking about the voltage law to say the sum of the voltage, the product of current to resistance, it must be equal to the supply. So the first loop, our supply is 5 volts. So meaning to say this V1 is going to be equal to, let's generate our formula. So from this, we are going to say V1, which is the supply of this loop, is equal to, we are now dealing with the voltage drops. So from here, I want you to check from point E to point F to point A to point B. We've got the same current flowing through, which is current 1. So we are going to use current 1 times the resistor 1. We only have resistor 1 in this loop. From here, from E, F, A to B in this branch. Then if you check from the branch from B to E, this branch, there is another current flowing there, which is current 3. And there is a resistor there, which is R3. So this is going to be current I3 times resistor R3. But remembering that this I3 we talked about, to say this I3 here is equal to I1 plus I2 already. We referred it on this part, so I'm not gonna rewrite this part. I3 is I1 plus I2. So let us use this formula to formulate our formula that is going to be in terms of unknown currents, I1 and I2. Then we move on to the other loop and do the same. So that is how you formulate these. Okay, so here we can even just take also for the loop 2, which is the loop from C to B to E to D. So that is from C to B to E to the point D and back to the point C. All right, so this is the loop that we're going to consider here. So on this loop, if you are to consider properly, I want us to check properly here. The same thing, just like the previous part, if you consider from the point E here to D to C to the point B, this branch here, this branch as we go up to B, there is only one current that is flowing there, which is I2, with only one resistance, which is R2. So meaning to say the voltage total, which is V2, is going to be I2 times R2, current times resistance. If we move from B to E, it is the same condition that we had in the previous part. B to E, we only have current 3 and resistor R3. So this is going to be plus I3 times R3, like that. All right, so this is what you're going to have from this loop. So let us have our calculations. Okay, so from the first loop, let us insert our values. We said V1 and our V1 is 5. So 5 is equal to I1. We do not have R1. We have got our R1, which is 4. So this is going to be 4 times I1 plus I3, which we said I3 is same as I1 plus I2. So this is going to be I1 plus I2 times the resistor R3, and our resistor R3 is 8. So from this, we can expand and have the final equation. Okay, so let us expand. 5 is equal to 4I1. We can expand by 8, the bracket, that is 8 times I1, which is going to be a plus. Take note here, we've got a plus. So it's going to be plus 8 I1. We move on to 8 and I2. So this is going to be a plus again. We've got a plus and a plus. So 8 times I2, which is going to be 8 I2 like this. Considering what we have, we can collect the like terms, I1 and I1. These are like terms. So you can consider this 4 plus 8, which is going to give us 12. So we're going to have 12 I1 plus 8 I2. So this we can formulate, we can say this is our final equation. Okay, so just writing, starting with our variables, that is going to be 12 I1 plus 8 I2, which is equal to 5. All right, so we've got our first equation. We can just leave it here. That is our first equation. So you can just leave at this stage. All right, let's consider what we have got from the second loop. Remember what we said from our second loop, we are going to have V2, which is we are considering this part of our circuit, our V2, which is 2 volts in this case. So this is going to be 2 is equal to I2 we do not have, but R2 we have. Our R2 is 6. So this one is going to give us 6 I2 plus, remember, this part of I3, R3, this part is the same as this part that we had before here, I3, R3. So we simplified this part. From this part, we got this part up to this stage. So this is what we got here from the calculation of I3, R3. So I'm not going to repeat this part. I'm just going to take as it is. So here we simplified up to this stage, which is at 8 I1 plus 8 I2. Yes, we can redo that. The calculations is fine. You can just restart. Still, you're going to have the same thing. All right, so let us combine here what we have. The like term. So I1 does not have a like term, but if you consider I2 and I2, these are like terms. So you can add 8 to 6, which is going to give us 14. So you're going to have 14 I2. All right, so these are the formulas that you have at end that you're going to use to calculate I1 and I2. By calculating I1 and I2, we are automatically having the value of either, because I3 is the sum of I1 and I2. That's why I'm leaving these equations in terms of what I1 and I2. We can't use I3 direct because we'll be having 3 unknown values and it will be difficult for us to solve, but you can actually do that. But to avoid that, you can just work with these two. So to calculate I1 and I2, that's where you ask yourself which method you are best at. Is it elimination method? Is it substitution method? Whatever method that you are best at, you can use that method, okay? So in this case, I'm just going to work with the elimination part. All right, so I'm going to work with elimination by substitution. I'm going to have my two equations. Let me have them here. The first equation, we have got 12 I1 plus 8 I2, which is equal to 5. Then this is our second equation, but just start with the variables on the one side. So we're going to have 8 I1 plus 14 I2, which is equal to 2. So this is what you're going to have in this case. All right, of which we can actually reduce our equations like this one, equation 2. We can reduce our equation 2 maybe by 2. If we reduce this one by 2, by 2, by 2, before we simplify, this will be 2 into 8, which is going to be 4 I1, 2 into 14, which is going to be plus 7 I2, is equal to 2 into 2, which is going to give us 1, of which you can just use the equations as they are. It's still fine because you are using a calculator, so there is no effect at all. So these are the two equations that I'm working with. So from these equations, you choose which part do you want to calculate, and that part is going to determine what are you going to eliminate. Like for this case, let's say I want to calculate I1. If I'm to calculate I1, that means I have to eliminate at that moment I2. All right, so that is the condition. We have to eliminate I2. To eliminate I2, you focus on the constant term, these two numbers here, you interchange them so that they will be the same, so that you can eliminate I2. So you can multiply on top with 7, then down here, we can multiply with 8, this number. So you want to make these two to be the same. So you multiply on top with 7, down you multiply with 8. You just interchange these two numbers, okay? So that means if we are to have this, we are going to have our final answer is 7 times 12, which is going to be 84, I1. 7 times 8, which is going to be 56. So that's 56, I2. 7 and 5, which is going to be 35. 8 and 4, remember I'm using this equation, so it's 8 versus 4, which is 32. I1, 8 versus 7, which is 56. So we've got 56, I2. Then we've got 8 and 1 in this case. This is going to give us 8. So if you have to take note properly here, we can eliminate I2 since these two are the same. I2, we've got 56, here, so we can remove this by subtracting. This is a positive, it's a positive, so if the signs are the same, you can simply subtract. So if you subtract, this will be 84 I1 minus 32 I1. So 84 minus 32, this will give us 52 I1, which is equal to, because here we have eliminated, if you subtract these two, it actually, this one and this one cancels. So meaning we are going to have 35 minus 8, and 35 minus 8, this will be 27. Remember what you're supposed to calculate here is I1, so you can divide by 52 both sides, by 52 both sides. That means we've got our I1. So 27 divided by 52 as a decimal, we are going to obtain 0.519 to 3 decimal places. That's 0.5192 and so on. So if you round to 3 decimal places, this will be 0.519 amps. So remember, it's current. So to find I2, you can substitute this value into any of the equations that we have got here. So here I can prefer this equation, one that I'm got here. So you can just any equation of your choice, all right? So you can substitute here. That is going to be 12 I1. So it's 12 times I1, which is our I1 here. It's 0.519 plus 8 I2, which is going to give us 5. So we can calculate I2 from there, all right? So multiply 12 times 0.519. This is going to give us 6.228 plus 8 I1, 8 I2, which is going to be 5. So you can transpose this to the other side, subtract. That will be a negative on the other side of the equation. So it's 5 minus 6.228. So this will be negative 1.228. So we can divide by 8. We can divide by 8 both sides. Thus, we are obtaining the value for current 2. So this will be a negative 0.1535 and so on. So this will be a 4 to 3 decimal places. So do not worry with the negative. The negative is just for direction, and that must be considered on our final answer. So this is our current 2, and this is our current 1. But remember that we are supposed to calculate this current, which is flowing through the resistor R3, and we said it's I3, which is going to be I1 plus I2. So you combine the two currents that you calculated here. So we have got our I1 and our I2, we calculated them. So therefore, we said I3 is equal to I1 plus I2. So we can substitute our I1 in this case. So that means our I3 is going to be I1, which is 0.519 plus I2, which is going to give us a negative 0.154 like this. All right, so this gives us the value of I3. So if you are to simplify properly, this is a plus and this is a minus. So you're going to have a negative at the end, and your answer is going to be 0.364 amps. So this is what you're going to have. That is the current through R3. That is I3. That is the current through R3. So this is the final answer that you are supposed to have in amps. And take note of the units, or current is measured in amps. So as you can see, guys, these are the typical questions that you might be having. But this one you can also revise on your industrial electronics N3. I think we talked about this, Kirchhoff's laws. So you can revise from there. But there can be other typical questions that you need actually to revise as much as you can. But for this one, that's what you can do. Okay, guys, that's it from Maison African Motives. Till we meet again.